see about OpenBMC difference, majority difference between OpenBMC and the traditional BMC or third party. Source code, user interface, we don't quite use IPMI. We treat OpenBMC as a server. And the security part, we leverage a lot of server security, use SSH, all the stuff, HTTPS. And authentication, we use the centralized certificate. And also the multi-node management are different inside OpenBMC. So this is the architecture presented last year. We treat the OpenBMC stack as 3 layers. One is SOC layer, which match to the BMC SOC. Then we have the board layer, which includes all the board-specific functions. Then we have the application layer, which are common to all the BMC implementation on different boards. So in the past year, we migrated to Yocto 1.8.1, and internally we already have OpenBMC running on 5 different boards, and we developed OpenBMC together with hardware board development. And also we deployed thousands of boards running OpenBMC in physical production network. So in the deployment side, we manage OpenBMC as server. So it's just another server. And we regularly push OpenBMC as software push, as other software like in Facebook. And due to the hardware limitation of the storage and the memory, we were not able to put Chef client inside OpenBMC, but we developed a tiny framework called Spectra, which is able to sync with the Chef client. And so that we use the same management system Chef to manage servers and also the OpenBMC. And we use SSH certificate to manage the access permissions. And we use RESTful interface for outside to access through information and the sensors. So next I will pass it to Robin to deep dive into OpenBMC on one of the board.
Thank you, DM. So yesterday you all heard Jason Taylor speak about NVM, and Chris explain a little bit about Lightning. For those who missed that, Lightning is basically our JBoss that has 32 PCI lanes going in, and then the switch fanning it out to 60 PCI lanes to the SSDs on the board. So each tray has 15 each SSDs, a total of 30, or you can have 60 by 2 SSDs. So why do we need BMC on Lightning? So there were some limitations and challenges on Lightning on how we do chassis management, since the NVMe enclosure management is not ready yet. For that, we used a BMC chip for doing the chassis management, getting all the fan speed, the sensors and those things. And for enclosure management, like updating the PCI config file, the switch firmware, the SSD firmware, sidebar information, and those things. And then for Lightning, it's a multi-host system where you can connect multiple hosts to a single chassis and manage the switch. But then since there are so many hosts managing the single switch, we needed an autonomous system that could do that. So and hence we have the BMC on that. Now there were some challenges with OpenBMC. Let's see what was the major one. So usually what happens is you have like a network connected to the BMC and you can access it out of band. But with OpenBMC, with the BMC on Lightning, there was no way we could have a sideband interface. The reason for that is there's no NIC on the chassis, it's just a bunch of flash. And then we, even if you put a NIC, the chassis would be managed as another asset, and then you couldn't really have one-to-one mapping to the storage JBoss and the host. So there were challenges on the infra side to do that. And as Tian mentioned, it's very difficult to run Chef and all those provisioning tools on a small controller of the BMC. I'm like, okay, and then what can we do? So we came up with different interfaces to the BMC. So we have the host and OpenBMC running on Lightning, correct? So one of them is having a USB connection from the host that runs to the BMC, and you can run Ethernet over USB. And once you have that thing running, you can either use SSH and RESTful interface to speak to the BMC one-to-one. And then you have the I2C bus going from the host BMC to the Lightning BMC. So in that case, you can do it in-band from the host itself, or you can access the Lightning BMC by bridging all the commands from the host BMC. This is a standard IPMI spec that you can use on this, on the host BMC, irrespective whether the host BMC is running a third-party BMC or OpenBMC. And then we also have an interface which so we have 16 lanes going in from the host to the PCI switch, and one of them goes to the BMC. So we plan to use MCTP later on, but then right now we don't support it. So I think I'll pass on to Sai on giving us an update on Yosemite.
Hi. Okay. So you have seen my colleagues talk about like how OpenBMC is being used on the networking, top of the rack switch, fabric switch, and also the storage. Now I'm going to spend some time on seeing how OpenBMC is used on the server side. So this is the Yosemite, the multi-node platform that we introduced last year. And this is a continuation of conversation that we had last year. So there was a question from the audience saying, can we run OpenBMC on the Yosemite? At that time, we have a working system with the traditional BMC, and we brought it up, and then it is working actually. After that, we started doing, can we run really OpenBMC on the multi-node system with all the server-specific interfaces? And then we did a POC, and it seems to be like within a couple of months, we were able to kind of bring it up, and then we can have the minimum set of features that are required for bring up. So we started doing that effort, and now we are planning, the POR is to kind of have OpenBMC on the Yosemite platform in the production. So if you see the Yosemite platform, we have the 4 servers sharing the same sled, and then they share the power and also the network infrastructure. So BMC has the NCSI connection to the network, and we use that for out-of-band management. From the user point of view, user interface point of view, there is a difference as before we have seen. The first one is like on the in-band side, there is no much difference. So it is still like IPMB to each of the node, and then we speak IPMI language. So BIOS can treat OpenBMC as a traditional BMC. It can get all the minimum supported set that is exposed by the OpenBMC to manage it. On the out-of-band, there's a lot of difference. So we don't have the RMCP plus protocol running on it. So it's purely a network, and then we run SSH and REST API. So those are the 2 interfaces that we provide to the user on the out-of-band side. So let's look at user interface. The first one is SSH. So once we get SSH, we have the complete Linux shell access. But we need some tools to kind of use different functionalities. So we have some bunch of tools, utilities that we develop, which user can use to manage the system. The REST API is another one. So it runs on HTTP or HTTPS for security. And then we have RESTful endpoints. I'll go into detail on that. So the first interface is the utilities. So let's look at some utilities like say flow information. So all these server boards and the site plan board and the network mesh card has this flow ID, and like that has part number, serial number, asset tag. So this flow ID util can get you the information in the user readable format, and you can also update it. The next one is power control and status. So for each of the server, you can get the status of whether it's powered on or off, or the status, and also you can control it. Like there are different ways to control the power. One is a DC kind and AC. So there is something called, we have a 12 volts supply going to each of the card. We can cut off so that we can even kill the 3.3 volt standby on the server. Our regular power off, which is like a DC cycle, is also possible. And we have a complete sled cycle, so where you can simulate a user going there and removing the complete sled out and then reinserting it back. That will clear even BMC state. The next one is serial over LAN. So it is like a SSH based. So you just use SYLUT and then tell which slot you want to connect to, and you can run parallel 4 sessions at the same time, and you get 4 servers managed at the same time. And then you can use Control X to stop the session. And also we have the history, like just in case if the host is hanging, you want to debug what happened before. We store the console output of the previous session actually, and then keep it there so that for debugging it will be useful. So that's the history feature. We keep monitoring the sensors, and then the sensor utility can provide the information like current values and also like thresholds. Since we're monitoring all the sensors, the logs will be logged into a file, and then log detail can be used to parse it and then show it. The firmware update, so we have a bunch of components like the CPLD, BIOS, ME, and all, which we can update using this tool. And on the front panel, we have a switch and then a USB channel which can be connected between external world and the BMC and the selected server. So we can use this command to kind of choose which USB you want to connect to. And also the identification, let's say if you want a tech to go there and then replace the server, we can use the identification command, which will blink some LED. And we have a configuration util to kind of pass some policies, like say power on policy to be last power state, always on, always off. The other tools are like fan control and then communication with Intel ME. We provided a transparent tool. So if you want to send any command to Intel ME for a given server, you can just send it. So there are a lot of OEM commands that you can send it using this. And the BMC firmware update is pretty much like having the root file system and a kernel image updated, copy it, and then secure copy the files and update it. So we are having tools which are doing wrapper tools with security and all. So on the REST API, so we have the design wise, we chose to have this resource model, which is simple, consistent, and discoverable. What it means is the schema has to be very simple, and then when you go to a resource, it should provide you a consistent interface, always available properties. And the discoverability, so you can be able to kind of go to one resource and then find out what else you can discover through that node. And we try to kind of keep the model as much as possible close to the hardware topology. So to meet that requirement, so we come up with 3 different attributes. The first one is the information, like when you go to a resource node, it should tell you like what it is actually. And it is a schemaless, so it just has a bunch of key value pairs, and user can define the resource node. Based on the resource node, it can define what keys and values make sense for that resource. And the next property is the actions. So some of the resources you can take actions, like say a server, you can do power on, power off, or RESTful shutdown. So those actions will appear in this array of actions that you can take on a resource. The last one is the resources itself, which is a links to the next discoverable resources. So I will show you with an example that how it looks like. So the model for the Yosemite looks like this. So once user at the top level, he does the API, he gets to know that it has a side plane board and a measurement card and 4 servers. If one of the servers is missing, he doesn't see it actually. He just sees when server 1, 3, 4 are populated. Once you go into one of the server node, it tells you it has a through ID, it has sensors and logs. So you can go further down and see what it has actually. So this allows us to kind of discover on demand and then browse through. But at the same time, it is a schemaless. So it just provides you that there is actions you can take, and then a list of actions, a resources list, and a key value pair, which is very opaque. It's like objects, blobs. So an example would look like root node has a root API, side plane board to show you like /API/SPB. and it has a BMC, and server board shows the example is server 3 to show you like what entities it supports. And a mesh card has this. The usage is also pretty simple, like you just use curl command to test it. Of course, you need, for security purpose, you need to pass all the credentials since it is a stateless system. The last one is the action that you can take a post to a particular resource, the power of server 3. Just to summarize, I think what we learned, like the architecture is pretty flexible. If you want to add anything, you can add it. It's a very open system. And it's easy to bring up a new board. Like within a couple of months, we were able to kind of bring up the Yosemite, which is supposed to be complex, like with multi-nodes. And the work is pretty much on the board-specific stuff, like where the SQL buses are. So you just need to configure them and then make it work for the particular hardware. So ongoing wise, we have this kernel, as Tian mentioned, it is like 2.6. We are moving to 4.1.x. It will be ready soon and be shared with the GitHub community. And then we are moving to 2500 series of AST. So we have the SDK, and then we are bringing in all the drivers from the platform. So our next platform will be based on 2500. The next steps, what we are seeing is the challenges. Some of the challenges are like driver stabilities. So typically, like our vendors, so they have the reference code, but it works most of the time. But some cases, if you stress it, there are cases where error scenarios, it doesn't, it's not stable actually. So we spend a lot of time to kind of make the driver stable, and we can use some community help for that. And then the tooling wise, like there are various phases, like the development wise, and then the deployment. Maintenance, like say firmware updates. So the tools are not that great, so we are still working on them, but we can use some help on that. But what we are seeing is a blockage is for developing, for anybody to come on board for OpenBMC development, they need some hardware actually. So typically they use the EVK, the vendor has a evaluation kit that can be used to bring up, like say kernel, U-boot, and then some sensors. But there is no way to communicate to your server to kind of check the BIOS kind of communication, etc. So the complete development can be done only if somebody has access to a full server hardware, which has completely the CPU and the infrastructure for talking to the BMC and all the sensors. So we think by adding a developer platform, it will accelerate the innovation so that any new people can come on board quickly and then they start contributing. So what I mean by developer platform is like having a baseboard with similar to EVK, where you have the BMC chip and with its all the sensors, PWM signals, all the GPUs, I2C stuff, and then having a COM Express connectivity. So the COM Express is a big standard for the small form factor, and then that has a bunch of IOs, like it has USBs, PCIe, SATA, and also I2C, etc. So which is you can treat that as a server which we are managing, and then we can do the features can be developed pretty quickly and validated and then contributed back. And we are working with a company called Portwell, and then they are committed to make this COMI OpenBMC carrier port for OCP. And they assigned model number, and it's in the works actually because the design is going on, and we'll be having some prototypes pretty soon. So we hope this will enable and accelerate the OpenBMC contribution, and then the community-wise can enable the acceleration. Thank you. That's it. Sure. Yeah.
Ask questions about
I'll just pop the microphone around. Can you
after the session?
After?
Is there a mailing list or is there like
Yeah, GitHub has the mailing list.
What's the, do you have data on the RAM usage profile for OpenBMC? For example, what would be the minimum amount of RAM that you would expect would be necessary?
For the RAM,
Yes.
it's right now we have. So right now we have 256 RAM, but we are using only about 70 meg.
17,
70 meg.
oh, 70 megabytes? Okay.
Yeah. The flash is about 32 meg. We are using about 16 meg.
See it getting much down from there?
We might go up actually with all the features that we are adding.
Well, if it's external memory, yes.
It is external memory. And on the storage side, we have a Python there. So that take about 2-3 megs. And if you remove the Python, you save about 2-3 megs on storage side.
You guys mentioned a REST API, and I didn't hear the word redfish. Did you consider redfish, or did you find that your own schema served your needs better?
So Redfish, we evaluated 1.5 years back, really, when it was very early. And then it seemed a bit complex to kind of begin with for the REST API implementation. So what we chose was we chose to go a path where there is a schema-less. So in the sense like we don't have any schema other than having a consistent interface or consistent properties. So inside the properties, like say a description, it can provide anything it wants, key value pairs. That's it. It's like very transparent key, schema-less storage. That's what we went through.
Is the schema that you used available on GitHub?
There is no schema for per se actually, other than these 3 properties you can expect for logs, for events, and for through ID. You get all these 3, but inside each one there is no schema actually. It's pretty much like free-form key value pairs.
All right, thanks.
Sure.
Are you going to publish the schema?
Schema.
Yeah, for the value pairs.
Right now, if you see, it's all in the code actually, so there is no proper documentation for the schema at least. So our idea is to kind of go through the 5 platforms that we already have and try to see if there is any common elements that we need, so we can publish a schema. We can come up with a schema which is like incremental, rather than kind of publish everything and then try to put the elements into to fit the schema actually.
Because it looks like it would be the next thing for the interfaces, right? It's
Right.
scalable interface.
To add to that point, so when we take this approach, we think about starting doing one to get an open experience, and then doing more to get more experience. Then we come back to see what we can make it common.
You mentioned that you couldn't fit Chef. I think it was on Wedge. What was your reason why you didn't use Ansible?
Sorry, which one?
Oh, did you think about using Ansible?
Sorry, I don't know that one. I don't know the answer. Because we use Chef internally in Facebook to manage all the servers. So that's the only thing we looked into. Hi, Chris.
I was curious, you guys are going down a hardware platform for distribution for lots of people to join. Have you ever considered the simulation side, like the QEMU part of that Yocto's SDK has?
So we know the Yocto is very powerful to provide the simulation on that part. I'm not sure about the actual hardware side, like sensor or I2C, all the stuff. And a lot of work we have been doing during this past year for bringing up 5 different boards are board specific. And we almost get the board boot to Linux immediately without very minimal change for all different boards. And then a lot of details to support different applications. I'm not quite sure how QEMU can help on this area, but if it can, definitely something we can do. But we saw a real hardware platform would be better for the community to do some development to play with it.
Okay. All right, thank you guys.
Thank you.
Thank you.